So, good evening and welcome to this basic electronics course. In the last class, we have covered full wave rectifier and related equations. We have shown how to obtain these formulas, especially the peak inverse voltage formula for the full wave rectifier. And here we have a final equation for the peak inverse voltage, which is equal to 2 times peak output voltage plus 0.7 volt, which is the diode drop should be considered. So this is the formula for to calculate peak inverse voltage. Peak inverse voltage is one of the important parameter of full wave rectifier and even half wave rectifier. We should know how much diode can withstand during reverse bias. What is the voltage it can withstand during the reverse bias? So that's very important. Without going to the bridge rectifier, if you look at just a full wave rectifier with the center tap, this is going to be the formula. So 2 times peak output voltage plus 0.7 volt drop. Now let's move to the solving problem example 2.6 from the text. Let us read the problem. I'll just read the problem for you. Show the voltage waveforms across each of the secondary winding and across RL when a 100 volt peak sine wave is applied to the primary winding in figure 2.36. Here we have a figure 2.36. As you can see, this is the primary winding as you are seeing here, and if the sine wave AC signal is applied and its positive peak is 100 volts and negative peak is 100 volt. This is the sine wave AC signal, and here we have a fuse here, and the transformer turns ratio is given. It is a 2:1. That's the turns ratio. And this is the center tap transformer. As you can see, there is a center tap which is grounded here for this transformer. And diodes used in this secondary of the rectifier is 1N4001. This is ordinary PN junction diode. 2 diodes are used, which will work like a rectifying operation. And finally, the current coming out is given to the load resistor, which is of value is 10 kilo ohm. And we measure voltage across RL with a polarity as plus and minus here, and that voltage is indicated as Vout. Vout stands for output voltage, and Vin is nothing but which is the input voltage given. And second part of the problem is we need to assuming a 20% margin, what minimum peak inverse voltage rating must the diodes have? We need to calculate. Given is 20% margin, we should assume it, and based on that we should calculate what is the peak inverse voltage rating that the diode must have. So those things are the part B. Now let us go for solution part of it. I hope you understood the problem, given problem. Here as we know that the turns ratio is given, so the transformer turns ratio is taken as a small n, that is the turns ratio 0.5. How do we get 0.5? Yes, you have to take 1 by 2. So turns ratio of secondary and turns ratio of primary. Probably if you can remember the formula for that, if n is going to be the turns ratio, so n of secondary divided by n of n means it is the number of turns in the secondary. These are the turns what we are considering. This is the turns what they have given in the transformer. How many turns we have in the secondary to the number of turns in the primary. So this is the primary turns. If you take a ratio of this, that gives me the n. In this case, it is given as 1 by 2. 1 is the secondary turns, and 2 is going to be the number of turns in the primary. Therefore, small n is going to be 0.5. So that is what it is calculated here. Small n is going to be 0.5. That is the transformer turns ratio. Small n we have calculated. Now we need to calculate total peak secondary voltage. What is the peak secondary voltage here that we need to calculate here? So for that we have a formula which relates number of turns ratio to the peak primary voltage to the peak secondary voltage. So we know that the formula n is nothing but peak secondary voltage to the peak primary voltage. This again relation between the voltage also is related to number of turns. The formula is a Vp of secondary divided by Vp of primary. Using this formula, we can cross multiply this to get the Vp secondary. So Vp secondary is nothing but n times the Vp primary. So Vp primary is given as it is 100 volt peak, that is going to be the 100 volts, and turns ratio we know n is small, n is 0.5. Just if we do calculation, that gives me peak secondary voltage as 50 volts. So we got to know what is the total peak secondary voltage. That is the voltage that exists from here to here. So this is the peak secondary voltage which we got to know, which is 50 volts. But here this is a center tap transformer. So therefore the total secondary voltage, peak secondary voltage what we have, that gets equally divided, assuming that this is exactly at the center tap. So here we will have a 25 volts in the upper part, and lower part will have a 25 volts. The 50 volts now get divided equally between upper and the lower parts. So therefore you will have a 25 volts upper part and 25 volts as the lower part. So let us now consider this upper part of the voltage, and then calculate, because here we have a positive and negative half cycles. The polarity will change accordingly in the secondary of the transformer. So what is given in the problem? Problem is, as you know, is asked about show the voltage waveforms. We need to draw the voltage waveforms across each half of the secondary winding. So for each half of the secondary winding, we need to draw the voltage waveforms, and across RL. So we need to again, when 100 volt is applied, what is the voltage across this we need to find out. So there is 25 volt peak across each half of the secondary. That's what we calculated with reference to the ground. So the output voltage has a peak value of 25 volts, and now because of diode drop, we need to subtract it in order to calculate Vp out here. So we need to subtract the diode drop as well. Suppose if it is a ordinary diode, then we should consider 0.7 volt as the drop across this. So once we subtract this 25 drop 0.7 volt from 25 volts, that gives me 24.3 volts. That's going to be the Vp of across RL. I mean the Vp out is the thing, but which is 24.3 volts. That is the voltage across it. Okay. So now we know that the peak output voltage across load resistance is 24.3 volts. Just have subtracted 0.7 from 25. That's all, nothing else I did. Okay. So now based on this, we can draw the waveform. As you can see here, this is now waveform drawn. So across each half of the transformer winding, you can see that the signal goes to the 25 volts peak starting from 0, and this upper part is 25 weak and minus 25. That is going to be the input signal. And across at each half of the transformer, this is the signal at each half of the transformer secondary winding. Okay, now at the output, we have the signal goes up to 24.3 volts. As we have shown already, the output is 24.3 volts. From 25 we need to subtract 25 volts, we need to subtract 0.7 volts. That gives me 24.3 volts. Okay, so that is the voltage. Signal will go positive peak, and again it comes to 0. Since it is a full wave rectifier, so signal can go all the way up to 24.3 volts. So this is the waveform, output waveform that need to be drawn. Okay, so now second part of the problem is we need to calculate the peak inverse voltage for each diode. We know the formula. Just can go through the formula here. Peak inverse voltage is 2 times Vp out plus 0.7. So we can use that. So Vp out is already known, which is 24.3 volts. 2 times Vp out plus 0.7. If you do the calculation, that gives me around 49.3 volts. So this is the peak inverse voltage of the full wave rectifier. And as it was stated, the peak inverse voltage rating should be at least 20% higher. So 20% higher of this gives me around 60 volts. So that is going to be the rating of the transformer that I should choose. The diodes rating should be chosen such that it can withstand up to 60 volts, though it is peak inverse voltage is 49.3 volts. Okay, so that's about the problem. And now there's again related problem. The students can solve the related problem on their own, similar to the problem. Now let's move to the next topic of interest is bridge full wave rectifier operation. Let us see. So far we have seen the full wave rectifier, center tap based full wave rectifier, and now we are moving to the bridge full wave rectifier operation. The main drawback of full wave rectifier is the two things which I need to highlight it here. The center tap problem. The number one is center tap itself is a problem, because these type of transformers, though we said that exactly the voltage should be upper half and lower half should be same, but it's very difficult to get the upper half and lower half voltage exactly same. So what we expect from center tap is the upper half part and lower half part, this voltage should be equal. Suppose in our previous calculations we got to know which is 24.3 volts, and lower half also we expect to 24.3 volts. Okay, so that's quite difficult to get because practical center tap transformer won't give this exact voltage, equal voltage. That is one issue with reference to full wave rectifier. Another problem is the center tap transformer is they are expensive, so that is the reason we won't use even to manufacture this center tap transformer. It is very difficult, very expensive. So therefore, we try to avoid full wave rectifier and move on to the new rectifier without using the center tap. That's what you are seeing here. This is the a bridge full wave rectifier. This type of rectifier doesn't use any center tap transformer. So let's go through the step-by-step operation of this bridge full wave rectifier. The bridge full wave rectifier uses four diodes, namely D1, D2, D3, and D4. It uses four diodes. Okay, connected as labeled as D1 to D4. And when the input cycle is positive, as in part A, this is the input cycle you are seeing here, the AC signal that is applied to the primary of the transformer with a fuse here. This is the AC source which is coming, and this is an AC cycle that is applied. During the positive half cycle, if you analyze, diodes D1 and D2 are forward biased. You can see the polarity here. When the positive cycle is applied, the polarity is minus here to the bottom and the plus to the top, and same polarity comes to the secondary, minus and plus. And based on this polarity, we can decide the directions of the diode and decide conditions of the diode. So we'll have here plus here, this will be positive, and the negative here. Just remove unwanted things here so that it becomes easy. So the polarity is plus here, therefore the positive will be here to the diode D1 and negative will be here, and minus comes here, therefore minus will be here, and plus will be the across D2. And here again, since it is a plus here, so we have a plus across a D3. Okay, this is a plus sign, and a minus here. And how about here? So this is a minus here, and because the minus comes here, the minus here and plus here. Now, based on the polarity that we have shown here, we can decide diode D1 is forward biased. So this is forward biased. Okay. And even the D2 is also forward biased. So which are shown in green color, of course. And we can see the other diode conditions here. D3 minus to the anode and plus to the cathode. This remains reverse bias. So this is D3 is reverse biased. And the same thing will happen for D4, because minus to the anode and the plus to the cathode, this becomes reverse bias. Okay. So we understood now for the positive half cycle, when the input AC cycle is this. So the here voltage which we have preferred is North American standard, so which is 120 volts AC, and 60 hertz is going to be the frequency, that is the sine wave. And when we consider, there is a fuse here which is very important, because whenever the huge current surge here, the fuse will break down. So fuse is used here. This is the fuse part, and when the positive half cycle comes here, this is the polarity, and we have seen the diode conditions here. And the diodes which are in green color, they conduct, they are forward bias, and diodes which are in pink color, they do not conduct, they are in reverse bias. Now let us decide the direction of the current direction in the forward mode. So if I start with the current direction here with the ground and end up with the ground, as we can see here, this is the direction of current. So it starts from D2, then through the transformer, then the current goes through the D1 because this is forward biased. Assuming diodes are ideal, that's one thing which I forgot to mention here is all diodes in the to analyze the circuit, we assume it as an ideal. What do you mean by ideal? So ideal diode in the sense whenever the voltage exceeds V is greater than 0, diode becomes forward bias. Let us give some notations to the forward bias as FB and the reverse bias as RB. Okay. So whenever the applied voltage here across the diode, the applied voltage exceeds 0, so diode becomes forward biased and it is turned on, current flows. Whenever the applied voltage is less than 0, so diode becomes reverse bias, and it is turned off. Here current flows, I exist, here current becomes 0, I is going to be 0. Okay, so I exist in this case. Okay, so that's how the current flows. So here we treat D1 and D2 as ideal diodes. So across them voltage drop is going to be 0. We don't have any voltage drop here, so 0 volt is a voltage. Diode doesn't consume any voltage drop, so therefore voltage across them is 0. So therefore the current direction is shown here. So current, as we have mentioned, that it starts from D2, then through the transformer, then back through D1, and it goes to the RL, and the voltage drop across RL is plus and minus. The polarity is shown here. This is the voltage drop, V out, output voltage. And as we are seeing here, the exact positive half cycle appears at the output voltage as a output voltage here, right? This is the output voltage. So this is what happens during the positive half cycle. So the conclusion here is during the positive half cycle, D1, D2 are forward bias, they conduct and they allow the current to flow through them. Therefore, the current exists in this loop. So current starts from the ground and then the D2, then through the transformer, D1, and then through the RL. So current, this is the path, the direction of the current that we have chosen here, and the exact positive half cycle. So we have analyzed only for the positive half cycle, say from 0 to T1 timing, whenever the 0 touches. So till that we have analyzed. So exact the positive half cycle appears at the output. So this is the analysis during the positive half cycle. And let's move to the analysis of negative half cycle. What happens? So the negative half cycle, whatever we said earlier, it is totally reversed. The negative half cycle, again look at the polarity here, minus to the upper part and plus to the lower. And again same as usual, this is 120 volts is the AC source and 60 hertz is going to be the frequency. And we are now analyzing from the timing the T1 to say here T2, the timing T2, between T1 and T2. So the negative half cycle, let us see the circuit, the behavior. So the polarity changes to minus and plus here, and as usual diode D3 now. Let us assign the polarity here, minus here, plus here, and minus here, and plus here. That is the polarity across T1. And for this one, we have plus here, minus here, and again as usual plus here, minus here. So D3 is forward biased, and write FB here for forward bias. D4 is forward biased. D1 is reverse biased. Let me write it as RB. So D2 is also reverse biased. So when the negative half cycle is applied to the primary effect transformer, same negative half cycle appears at the secondary effect transformer, and this voltage makes D3 and D4 as forward biased, D1 and D2 as reverse biased. So therefore the current direction, as you can see here, it starts from the ground through D3, then through transformer the current goes through D4 to the RL. And if you notice the direction of the current here across RL, the same direction as you can see here, between the top to bottom the current is flowing. And even during negative half cycle also current flows from top to bottom. That means even though we applied negative cycle at the input, but that has become now exactly the same as the positive half cycle. So this we got it during the positive half cycle, and the second pulse what we have got is during negative half cycle. That means the negative half cycle at the input is converted to the positive half cycle at the output. So if you consider for remaining cycles, so this is 60 hertz sine wave. We have shown only for one cycle here, and repeating this for the other cycles, you get complete waveforms in this way. Okay, so the positive cycles keep appearing at the output of the full wave rectifier. This is the operation of the full wave rectifier, full wave bridge rectifier here. So all these things has been explained. So the students are advised to go through the content described here. Now let us move to the analysis of bridge output voltage. So let us see here. A bridge rectifier with a transformer coupled input is shown here. During the positive half cycle, the total secondary voltages, diodes D1 and D2 are forward biased. We have seen that. Neglecting diode drops because we consider diodes as ideal. So secondary voltage that appears across the load resistor, which is we need to the same, because whatever here we have considered for the positive half cycle. So the peak output voltage Vp out is equal to the peak secondary voltage. What do you mean by that? So the peak output voltage here, okay, this peak output voltage what we have seen here is exactly equal to the peak secondary voltage. The voltage what we get here, it exactly appears at the secondary here. Okay. The same is true even for the, this is though we have discussed for one half cycle and other cycle, the D3, D4 becomes reverse bias. Therefore, whatever the voltage appears at the negative peak, it will be the Vp secondary. Okay, the same secondary voltage it appears at the secondary voltage, but direction is same in both the half cycles here. Okay, and now let us calculate the diode drop. Considering the diode drop, the peak output voltage is nothing but the peak secondary voltage, that voltage out that peak voltage that appears at the secondary, minus 1.4. The reason is the two diodes are always going to be in series with the load resistor. As you can see here, either when the D1 and D2 are conducting, you can see when these two are conducting, the current direction is like this, D1 and D2 and RL. All three elements will come in series, just like this. So if I want to write me a diagram here, so here if I treat this as a D1 and I have a D2 and there will be a resistor, all three comes in series, okay, which goes to the ground here. So this part is tied to the ground here, right? This is a ground, one part which is grounded. If I treat this as a D1 and this as a D2 and this as an RL, all three comes in series. So these are in series. Okay, that's what it is discussed here. Okay, so therefore, so two diodes comes in series. We know that each diode voltage drop across it is going to be 0.7. So therefore, the two diodes comes in series. So it is going to be 1.4 volts. The sum of two diode drops. So therefore, peak output voltage is equal to the peak voltage of secondary, and we need to subtract two diode drops from the secondary peak voltage. That is the peak voltage that appears at the output of load resistor. Okay. Okay, so let us see that now. The next circuit is going to be the ideal conditions. When the ideal diodes are considered, you can see here, this is the, we should not consider any drop across them. So this is for the positive half cycles. D1 and D2 remains forward bias, D3 and D4 remains in reverse bias, and when the cycle changes, the reverse. Okay, so D3, D4 becomes forward bias and D1, D2 becomes reverse biased. But look at the ideal diodes. When the ideal diodes is considered, the peak output voltage is exactly equal to the peak voltage of the secondary. The peak voltage of secondary, whatever it appears, that exactly appears across the load. Okay. Next, when we consider the practical diodes, okay, so then 0.7 volt has to be considered across the diode. As you can see here, this is for the positive half cycle. So therefore, this formula here doesn't remain as Vp out is equal to Vp sec secondary. So the formula changes now. The peak output voltage is equal to the secondary peak output voltage minus the 1.4 volt. So because that, as I mentioned already, the two diodes will come into the conduction. Therefore, the 1.4 volt should be summed up, and so 1.4 volt should be subtracted from the peak secondary voltage. Okay. Just like previous calculations, we need to even work out on the calculation of peak inverse voltage. Peak inverse voltage definition is how much diodes can withstand when they are not conducting. Okay, so that's very important. That is the definition of peak inverse voltage. And let's assume that D1, D2 are forward biased during the positive half cycle, and we need to examine the D3, D4 because they remain in reverse bias. So now, instead of worrying about D1, D2, they are already conducting. Look at their circuit when the positive cycle is applied here. Okay, so D1, D2, they are conducting. Since they are ideal diode, we need to look at what is the peak inverse voltage. So peak inverse voltage exactly becomes equal to Vp out is exactly becomes equal to Vp secondary. How do we know that? So let's assume that the voltage across this diode is going to be peak inverse voltage. The voltage that appears across this when the D1 is conducting and D2 is conducting. Simply, if you can, because here this is conducting 0 volts appears, and this is when the diode is in ideal condition. So this becomes like a short circuit. This is also short circuit because ideal diode that doesn't have any voltage drop across them. Internal resistance of the diode is going to be 0. Therefore, when the diode is conducting, they behave like a short circuit. Even D2 also behaves like a short circuit, whereas this behaves like a open circuit, right? This behaves like a open circuit. So we need to calculate what is the voltage across the diode which is not conducting. So now this ground is straight away plugged here. Now if you apply KVL in this loop, so if you apply KVL, that's minus. I start from here minus to plus. It is minus PIV plus. This is drop across. This is VP out. So let us consider VP out. That is equal to 0. And if you simplify, if you transfer to the other side, the peak inverse voltage becomes just a Vp out. So this is the peak inverse voltage of a bridge rectifier for ideal diode. Okay, let us now work out the same thing for the practical diode. Same thing you are seeing here. The peak inverse voltage of the ideal diode is just a Vp out. Just now we have calculated it. And for the practical diode, the formula is given here. The peak inverse voltage for the practical diode is Vp out plus 0.7. Let us work out how do we get this peak inverse voltage as Vp out plus 0.7. Again, as usual. So here we treat diodes as practical. So therefore, across them there is a voltage drop of 0.7 volt, and here also we have a voltage drop of 0.7 volt. That means here we have a voltage drop of 0.7. So if you apply KVL here, so we get plus 0.7. I start with ground. So this is a plus. I start with ground here plus 0.7 minus PIV. I go through this loop. Starting from here, I go and end up with the ground. So PIV plus minus PIV plus the voltage across the load resistance is plus and minus we have, and this is going to be Vp out. Vp out, that's equal to 0. This is the Kirchhoff voltage law, and what we want is the PIV. So PIV, if you transfer to the other side, you get equation as a PIV equals Vp out plus 0.7. That is the peak inverse voltage of this practical diode. Okay, so the same thing is shown here. So we understood how to work out the peak inverse voltage for the practical diode. Okay, so that's about the peak inverse voltage, and we'll take up one problem based on the bridge rectifier. Example is going to be the 2.7. Okay, so determine the peak output voltage for the bridge rectifier. Here the bridge rectifier is given in figure 2.41. That is the figure, and assuming the practical diode model. So here it is told to assume. So first of all, the circuit is given, and what type of diode it is said. It is a practical diode. Practical diode means across diode there will be a voltage drop which is 0.7. If D1, D2 are conducting, there will be a voltage drop of 0.7. In the next negative half cycle, if D3, D4 are conducting, the voltage drop across them will be 0.7 volt. Okay, assuming practical model, what peak inverse voltage rating is required for the diodes? We need to calculate what is the PIV rating required for the diodes. And transformer is specified to have a 12 volt RMS secondary voltage. Across this RMS voltage is given. Root means square voltage. Secondary voltage is given as 12 volts. And for the standard 120 volts. So 120 volts is the AC input source applied at the primary that results in secondary voltage, as it's not given as a peak here. Instead of that, they are given as RMS voltage. So the formula to calculate that is given here. So secondary peak voltage is 1.414 times the RMS voltage. RMS voltage is given as 12 volts. We can substitute it here. So 12 into 1.414 gives me 17 volt as the peak secondary voltage. That means across this I'll be getting 17. This voltage here is 17 volts. 17 volts. Sorry. So I have here 17 volts. That is the peak secondary voltage. Now we need to calculate peak output voltage. We can use the formula that we already shown to you. VP out. You can just have a look at. VP out is here. VP out is equal to VP sec minus 1.4. So I'll use the same formula here. VP out is equal to VP sec secondary peak voltage minus 1.4. So VP out, we need to calculate it. So VP secondary is 17 volts. We have just now got it. Minus 1.4, the two diode drops, that gives me 15.6 volts. So across this, I have a voltage of 15.6 volts. That is the VP out. Okay, next we need to calculate the peak inverse voltage of the diode. Peak inverse voltage of the diode, as we have just shown the formula. So peak inverse voltage is VP out plus 0.7. This is for the practical diode model. So let us apply that. VP out plus 0.7, that is the formula. VP out is 15.6. This value is 15.6. 0.7 is going to be the diode drop. That gives me 16.3 volt as the peak inverse voltage. So this shows that the diodes has to withstand, each diode has to withstand 16.3 volt as the negative voltage, across them, so that diodes doesn't burn out. Okay, with this voltage, we have to limit it to this voltage. So PIV rating must exceed this value. The rating what we choose, whenever we choose a diode, the rating of that must exceed this. We should not exactly stick to this 16.3 volt value. Okay, so so that is what the PIV rating is. 20% extra, of this value seems to be good while choosing the diode. Okay, so that completes the rectifier part, and now we are moving to the next part as regulators, and even filters. We need to discuss these two topics. First, let me cover the filter, and later on we will move on to the regulators. So what do you mean by filter? So far we have discussed about rectifier. So first we have talked about transformers, which will step down our AC input voltage to a smaller value. Then we have discussed about rectifier. Okay, rectifier, we discussed about center tap. Okay, and then we covered bridge rectifier. Okay, now we are moving to the filter, because the output of the bridge or the center tap rectifier is going to be just a pulsating DC, not a complete 100% DC. So we need to use a additional circuit to smoothen the DC output of a rectifier circuit. So when in the process of converting from AC to DC, AC means it's a signal that is fluctuating in nature. Okay. So this is a AC signal, and we want DC which is constant with reference to time. Okay, so this is a DC voltage. Okay, while getting this from AC to DC conversion, so the circuit what we used, rectifier, it doesn't give 100% DC flat DC voltage because of diode which produces only the pulsating type of DC, not a complete DC. We need to use additional circuit called as a filter. What filter will do? Filter eliminates fluctuations in the output voltage of the either the half wave rectifier or the full wave rectifier, and it try to produce the constant level DC voltage. That is the role of a filter. Okay. Now, if you look at electronic circuit, example is laptop, mobile, or whatever, those are called electronic circuits. What they want it? They want a constant source of DC voltage. They don't want any fluctuations. What we have seen in the rectifier, like just a positive half cycle. They don't want such type of varying DC voltage. They want a constant DC voltage, constant source of DC voltage. Okay, and even the current to provide proper biasing, to provide the proper power and the biasing, and even for the proper operation, the such type of the applications need a constant source of DC voltage. Now, how to get that constant source of DC voltage? It is not possible from the rectifier alone, and even from the transformer. Transformer just itself steps down. That's all here. but even rectifier alone is not suitable for that. So we need to use a filter. So let us see now here. Filters are implemented with capacitors. So capacitor is again an electronic component that is used at the output for the output of rectifier to get the filtered signal here. And later, to have again a smooth DC voltage, just as I've shown here, we need to even use voltage regulators or regulation for the output of the filter. Even filter output is also not 100% DC. We need to use regulators. But regulators are available in the integrated circuit form. Okay, so in IC form as voltage regulators. One can prefer depending on the output DC voltage what we need. You can select the integrated circuit. A voltage regulator prevents any changes in the filtered DC voltage. Sometimes input voltage may change. There are variations in the input voltage, or sometimes the load can change. Load can be any type of loads, either zero load or higher load. Load can be varied. RL can change, or input voltage can change. For all these things, okay, the regulator provides a constant output voltage. We'll see that in a short file. How our regulator works and how it can provide a constant output voltage irrespective of input voltage change and the load resistor. Okay. Here we are going to explain a terms called as ripple voltage. Ripple voltage nothing but amount of AC present in the output of the filter that we'll call as a ripple. Ripple is nothing but AC component. Strictly speaking, ripple has to be zero, but unfortunately the filter produces small amount of ripple. And we'll calculate the formula for the ripple factor. That's very important. And we'll talk about how to apply this, the calculate ripple factor for both half wave and full wave rectifier. And then followed by, we have a term called a surge current, how to minimize the surge current whenever the power is turned on, AC power is turned on, we expect the DC voltage, to appear. But there is again, initially it causes some huge current that goes through the circuit, and that leads to the surge current. We'll see how to minimize that, and how to choose the current, the fuse to block this, heavy surge of current. And again, two parameters are important in the regulators. The one is the line regulation and as well as the load regulations. Whenever the load changes, how exactly the output voltage is maintained constant. That's what load regulation will decide. And line regulation is whenever the input voltage changes. To what extent, change in the input voltage is allowed so that output voltage remains constant. That is decided by the line regulations here. So these are the two important terms one need to know with reference to the voltage regulator. Okay, now let's take a look at different rectifiers what we have discussed. In most of the power applications, 60 hertz is the AC power supply, and we expect constant DC voltage at the output. But here the problem is, the half wave rectifier provides just a 60 hertz pulsating DC output, whereas the full wave rectifier, either the bridge or the center tap rectifier can provide frequency twice the frequency of input that we applied. That shortly we will understand it, how it gives you twice the frequency. Half a rectifier, just at the output of a half a rectifier is just we get a 60 hertz, whereas at the output of a full wave rectifier, either center tap or bridge, we get output as 120 hertz, twice the input frequency that we applied. Okay, that need to be filtered, of course, because we can't assume this as a positive off cycle as a DC. So we want to have a constant voltage, something like this. That is the DC voltage, instead of having this pulsate. This is called pulsating DC. It's already labeled here. You can see here, pulsating DC output. It's not a complete 100% DC output. It's a pulsating DC output. Okay, in figure 2.42, which shows filtering concept, for the full wave rectifier, okay, to smooth the output voltage waveform. So here, without filter, this is a rectifier block diagram. We are not showing any circuit diagram here. It's just a full wave rectifier block diagram, and the input is going to be the sine wave, as we can see here. Is the AC cycle, AC input that is applied from the transformer. And if I am using either this can be of a center tap, though it is not shown here. This can be of center tap. It can be of the bridge rectifier. Okay, whatever we are using, either center tap or bridge rectifier, the output waveform is a pulsating. All negative cycles have become now positive half cycles. Okay, so this is the pulsating DC waveform what we're getting from the rectifier. Now to convert this, to smoothen this, we need to use additional circuit called as a filter here. So for this circuit, we are just connecting here at the output of a filter an additional circuit called as a filter. Okay, now let us see, because this section deals with only the filter. We already discussed about full wave rectifier, how it works, different types, and what is the waveform here. We have already seen that. And this is a rectifier block diagram with filter. And now you can see inside this, as I told you, that capacitor plays a key role in the filtering operation. So now capacitor inside this, it will, whenever the positive cycle comes here, it will charge, and whenever the input cycle falls, it will discharge. We can see here the charging, discharging, charging, discharging, this type of the wave at the output of the the filter. This somehow it is able to produce the waveform of this nature. Okay, not exactly the same as DC, but to some extent it is giving output waveform same, nearly same as the DC voltage. Okay, now let us see that how this filter circuit works. For that, we have taken one simple filter as capacitor input filter. So we'll show the circuit diagram. Before that, let us go through the theory. The filter is simply a capacitor connected from the rectifier output, which goes through the load resistance. Okay, so we will see how this filter functions for half wave and as well as full wave rectifier. Let us see, try to understand the basic principle. We will use half wave rectifier to illustrate the basic principle, and later on we are going to expand the filter for the full wave rectification. Okay, so let's go through the circuit here. This is going to be the filter circuit. Okay, so for the half wave rectifier, and how this filter circuit works, let us see that. Initially, when the positive, this is going to be the AC signal, that is the output of transformer. When the at the T naught, as you can see, that input AC cycle is rising, it all the way it goes to the peak of the input, the VP in, that is the peak of the input voltage. Now, as when the input signal rises, we have connected here a capacitor, and voltage across capacitor is taken as a VC. And as we can see here, this is the voltage how it capacitor charges. Capacitor is energy storage element. Whenever the voltage is provided to that, it charges and discharges. When voltage is provided, it charges. When voltage is not provided, it starts discharging by identifying the suitable path. So now initially we started with T naught, all the way it has gone to VP in. Now diode becomes on, because it is forward bias. Initially, let us assume this as a ideal diode. So as we said, when the inputs start rising, the diode becomes a short circuit. So diode, it is conducting forward bias. Now capacitor keeps charging. As we can see that voltage across capacitor, it builds up. Okay, it rises to the VP in value. If it is a practical diode, then we need to subtract the diode drop of 0.7. That's what we did here. Now voltage across capacitor is, suppose if it is peak is going to be say 5 volts, and now voltage across capacitor is 5 minus 0.7, that is going to be 4.3 volt. So that is the voltage across capacitor. So capacitor, let's assume that it has been charged to 4.3 volts. Now let us see that once capacitor is fully charged to 4.3 volt, this will act like a source. Okay, now when the input is, now as we can see, input is dropping. Once it drops here, now what happens to the voltage across capacitor? The voltage here, whatever it has been raised, charged to 4.3 volts with the polarity as plus and minus, this voltage itself now it reverse biases this diode and turns off this diode. Okay, now diode becomes half whenever the input falls. Here voltage reduces, and here voltage remains as 4.3 volts. Okay, so therefore when the input drops here at the anode, if it voltage drops, but here the voltage already it has raised to 4.3 volts, therefore voltage across capacitor is 4.3 volts. So now this voltage has made diode as off, and now capacitor start discharging through this path. Okay, so the discharging path is now shown in the next waveform. As we can see here in this circuit, the diode is off, input is falling from the peak, and it goes all the way to negative, and again it rises, and during entire this cycle from peak of the positive to the till it reaches the first quarter of the next cycle. So you can see here diode remains half, and capacitor now it is discharging. This is the discharging. From here onwards, capacitor will discharge slowly. It is discharging, as we can see here, till here the input cycle is shown. Till that, capacitor will keep discharging to the load resistor, and this is the pink color loop that is shown is the discharging the current. Okay. And now let us look at here what happens when the again another cycle comes here, because here cycle has been completed and is the first quarter of the cycle. And again here, when the voltage here, when the capacitor keeps discharging, voltage here starts falling, right? So earlier we assumed it voltage as 4.3 volts. Now 4.3 can become 4 volts, 4 can become the 3.5 volts, 3.5 can become 3 volts. It keeps dropping. So this is capacitor discharging. So by the time it start discharging, what happens? Another cycle comes here. Voltage it goes beyond the 4.3 volts, and again the 4.3 volts here will charge the capacitor to the higher value. So you can see here again capacitor charges builds up, and again once it is again input is falling, capacitor start discharging. So this charging and discharging, charging, discharging, this is going to be a cycle which creates a DC voltage at the output. So a small amount of variation exists that we call as a ripple, and slowly by using some effective capacitors and using a voltage regulator, this variations in the charging discharging can be reduced. Okay, the same thing has been explained here, and I advise the students to go through that. And what is important is nothing but how much time capacitor tries to know what is the discharging time constant. We can see that capacitor discharging time constant is obtained by RL into C. So right here, this is a discharge time constant is decided by how much time capacitor takes to discharge is decided by a product of RL into C. So in the circuit, you can see here, this RL is here and the capacitor is here. This is a capacitor. The product of these two will decide how much time capacitor is going to discharge. Okay, so this is a time constant. Okay, discharging time constant is the product of RL into C. Okay, so that is the time constant, which is very important. Now let us have a look at waveforms produced with a small capacitor value. So it's a ripple voltage. As we can see, capacitor quickly charges. As we can see, initially when the voltage is raised, capacitor keeps charging. It charges immediately. Slow discharge happens because see here, because it depends on, as I told you, that it depends on the RL and the C value for discharge. Slowly it will discharge. By the time it discharge and goes reduced to it can't become zero because another cycle will come in, and again it charges and again discharge, charge, discharge. This is for the half-wave rectifier with smaller capacitor value. And here you can see that with the larger capacitor value, how exactly uh, the, the capacitor is going to be very slow in discharge. Here it's going to be very fast in discharge. Okay, so slope is reduced here, but here it's going to be fast because of larger capacitor value used. The smaller will be the ripple in this case, and here larger is going to be the ripple. So these are the two waveforms of both are for half-wave rectifier, and filtering is shown here in these two waveforms. Okay, so and as I was telling you that the output of full wave rectifier is frequency is going to be twice the half-wave rectifier. As we can see here, this is going to be the one period of half-wave full wave rectifier, and this is going to be one time period for the half-wave rectifier. And now we can see that in the within the time period here, the two pulse can be seen here. So therefore, so two times the time pulse here is nothing but the frequency becomes a double when you see that two pulses appears in the one shot. Okay, so that frequency doubles in the for the full wave rectifier here. Okay, for the f of full wave is two times the f of half wave of wave. Okay, so that's the analysis, but slope of the capacitor discharge rate almost it remains the same. This is going to be the discharge rate. Okay, only thing is when we increase the capacitor value, then only this slope can be altered. Otherwise the slope remains same. And now we have an important parameter called as a ripple factor. Ripple factor is an indication of the effectiveness of the filter, and it is defined as VR peak to peak by VDC. Numerator is nothing but the AC component, and the denominator is going to be the DC component. We expect VR peak to be as small as possible and DC to be as large as possible. Okay, in fact, the ripple factor need to be as small as possible. A rectifier is the filter is said to be very good when the ripple is very less. Okay, so ripple factor is very important parameter for the filter circuit. So now let us see what is this definitions. VR peak to peak is the peak to peak ripple voltage. This is the numerator part, and VDC is the DC average value, DC value or average value, both are same for the filter output. And as it is already told, lower the ripple factor, the better is going to be the filter. The ripple factor lowered by can be done by the increasing the value of the filter capacitor and even the load resistance. Okay, you can make R as small as possible by increasing the capacitor value, or you can also increase the value of load resistance here. Either any one of method we can just decrease the ripple factor value. And here we have a waveform to show both the AC and the DC part. And this is the output of the filter circuit. As we have seen, capacitor keeps charging and discharging waveform. We have seen this at the output of the filter circuit. And here this pulses what we have seen peak to peak is nothing but labeled as VRPP. This is a peak to peak ripple voltage, and this is the rectified peak voltage from zero level to the peak of this. This is called rectified peak voltage, and the DC voltage is nothing but the average value of this pulses. Okay, from zero level all the way up to here. This is the DC voltage. Now to calculate ripple, we need to have a peak to peak value of this. We are peak to peak, and the DC of this. The ratio of this and this gives me the ripple, and we expect that to be as small as possible. So the full wave rectifier with the capacitor input filter approximates peak to peak ripple voltage. We are peak to peak. The DC value of the filter output voltage is VDC, and variable this is VP rect is nothing but it's unfiltered peak rectified voltage. We already explained that. R into C, if it increases, then the ripple voltage can be decreased and the DC voltage can be increased. Now let us work out the formula for this. This is a relationship of ripple voltage, peak to peak ripple voltage to the frequency, resistance, load resistance and capacitance value, and VP rect is nothing but unfiltered rectified peak voltage. So in order to find the VR peak to peak, we should know the capacitor value and load resistor value. And DC voltage can be calculated by subtracting 1 minus 1 by 2 times FRL into C times VP rect. This is the unfiltered rectified voltage. Knowing these two values, we can calculate AC component, the ripple voltage, and the DC value, and that helps me to calculate the ripple factor R, which is nothing but ratio of VR peak to peak by VDC. And now let us work out one problem based on this. The example is 2.8. Determine the ripple factor for the filtered bridge rectifier. That is the problem with a load as shown here. This is the bridge rectifier circuit, and here we have a capacitor of 1000 microfarad capacitor. Load resistance is 230 ohm, and AC input voltage is given as 120 volts, 60 hertz. This is a primary of a transformer. At the secondary, we have VP secondary voltage, and this is a bridge rectifier circuit. And transformer is ratio is 10:1. That's a transformer. So we can calculate secondary voltage if I know the turn ratio. Turn ratio becomes 1 by 10, 0.1. And before that, let me calculate what is the peak voltage of the primary. Since it is RMS value, we can use RMS formula to calculate peak voltage of primary. To calculate this voltage, we use this formula 1.414 times RMS voltage. This 120 volt is the RMS voltage. So substituting here and multiplying with 1.414 gives me VP peak voltage of primary. The voltage here is going to be 170 volts. So though 120 volts is RMS voltage is given, at the peak primary voltage is going to be the peak voltage is going to be 170 volts. Now similarly, we can calculate what is the voltage at the secondary here. To calculate peak secondary voltage, we can use the turns ratio given here. So N is nothing but it is 1 by 10 is equal to 1 by 10. So 1 by 10 gives you the 0.1 times the primary peak voltage, which is 170 volts. That gives me 17 volts. So voltage here is now it is 17 volts. So that is reduced because diode requires smaller voltage. So now let us calculate what is the frequency of the full wave is going to be the 120 hertz, and using this we can calculate what is the ripple peak ripple voltage. So peak to peak ripple voltage is given by 1 by F RL into C times Vp of rectified signal. We can substitute all the values. Frequency is 120 Hertz for the full wave. 220 ohms is the RL, and the C is 1000 microfarad given, and unfiltered wave which were calculated, rectified peak voltage is 15.6 volts, and this reduces to the value of 0.591 volt. Now, then we can calculate the approximate DC value or average value. VDC is 1 minus 1 by 2 F RL into C times unfiltered rectified peak voltage that you can substitute here. 240 Hertz, that's going to be the 2 times CF, and RL and the C value, and this is going to be the rectified peak voltage 15.6. Okay, so that if you simplify this, the value is going to be around 15.3 volts. So this is the amount of DC voltage that we are getting at the here. So the DC voltage what we are getting is 15.3 volts. That is the DC voltage that we get. But what is the amount of AC present here? It is a 0.591 volt. So this is the DC value is 15.3, and the AC value is 0.5. Write it here, 591. That is going to be the AC voltage. That's very less, okay, because capacitor used is very high value, 1000 microfarad. So now you can calculate ripple factor. Ripple factor formula is VR peak to peak by VDC. So 0.591 by 15.3, that gives me 0.039%. Roughly it is a 3.9%, that is the amount of ripple. So it's very less compared to the without filtering the ripple. You can measure the ripple without filtering, that will be huge value. So in that context, this ripple is very less after filtering. Okay, and there's a related problem. Students are advised to go through the related problem. And now let us look at what is the surge current in the capacitor input filter. So now here we have a complete circuit of bridge rectifier with a transformer input. Let us now work out what is this surge current here. So this is the current. This is a bridge rectifier that is shown in this context. Is now for the positive off cycles, diode D1 and D2 are conducting, D3 and D4 are not conducting. They are in the reverse bias, and here we have a capacitor which is acting like a filtering doing the filtering operation, and we have an RL. And let us try to understand what we mean by the surge current. Before the switch is closed, the switch is a fuse here. Okay, here we have a switch, not a fuse. We have a switch here which is controlled, and before that is closed, the filter capacitor is uncharged. The capacitor what it is shown is not charged at all. Voltage across this is 0. Now instantly if the switch is closed, what happens now? Voltage is connected to the bridge. Whatever the voltage we apply here is connected to the bridge, and now the capacitor which is uncharged, okay, that now started charging now. But now question is, now in the beginning what happens? In the beginning, when the sudden voltage is given, AC voltage is applied to the capacitor becomes a short circuit here. Capacitor role is now it works like a short circuit. It becomes like a short circuit immediately when the power is turned on. And now what is its impact on the other part of the circuit? And now current, because as we know that if I treat diodes as ideal, the complete diodes acts like a short circuit. And now as you can see that this point now becomes like a ground, because this is a short circuit. The ground is now here. When the ground is here, now this is working like a short circuit. Now look at here, now this is a short circuit, ground back here. Entire circuit becomes like a short circuit. Okay, that this produces initial surge current, and now I surge, though through the two forward bias diodes which are D1 and D2 namely. The worst situation is when the switch is closed at the peak of the secondary voltage. So what do you mean by that? When the switch is closed, when the signal is at the peak here, at that time huge current will surge back to the circuit, and the chances are there where we may lose the complete circuit, because of maximum surge current happens when the switch is closed exactly at the peak at this particular point. Okay, so that leads to the huge damage to the entire circuit here. Sometimes when the sudden surge happens, the fuse may break out, but you must choose fuse with the proper rating. The fuse must be chosen, nearly 20% of this rating primary current. To choose the fuse, what should be the rating? Here we have a calculations. The input voltage by the RMS AC voltage that is applied, that will give you the current. What is the power that is input power applied, and based on that we can decide the primary current. Depend If I know the input power, I can calculate what is the primary current, and based on that I can choose the fuse here. And it is always suggested to choose 20% larger than the primary current here. Larger the fuse capacity we choose, then the chances of losing this circuit is very less. Okay, that's how the surge current the propagates through the bridge rectifier circuit. Now last part is the voltage regulator. Voltage regulators are very important element in smoothing the output voltage. Filters, they have certain amount of ripple that can be reduced from the rectified signal, but the most effective is going to be the combination of capacitor input filter with a voltage regulator. A voltage regulator is connected to the output of the filter rectifier, and it maintains a constant output voltage or current even though there is a variation in the input and the load current here. And even sometimes temperature variations also causes the variation in the circuit in the current levels here. So that can maintain constant levels. The voltage regulator and capacitor filter can maintain a constant voltage, DC voltage at the output here. The capacitor input filter reduces the input ripple. The regulator also brings to the acceptable level whatever the application needs here. The combination of large capacitor and a voltage regulator helps in providing a excellent DC power supply. Now, question is, now the regulators are available in the form of an IC as it is shown in the diagram here. Most regulators are integrated circuits and have got three terminals: an input terminal, output terminal, and reference voltage. As you can see here, there is a reference voltage, an input terminal is here. This is available in the form of an integrated circuit IC form, and it has got one more output terminal here. Totally, it has got three terminals here. The input to the regulator is first filtered with a capacitor to reduce the ripple to less than 10%. Whatever the filter here should be brought up to the ripple value to less than 10%. Then only this regulator can act effectively. The regulator reduces the ripple to a negligible amount. In addition, most regulators have internal voltage reference for short circuit protection. Just now we have seen that surge current protection, and also it will have a thermal shutdown circuitry also. All this, everything is inbuilt within this voltage regulator. There have been variety of voltages including positive and negative outputs. They will always comes with a different reference voltages VZ, either positive VZ or negative VZ value. There are different types of output voltages. Can be designed for variable outputs also with a minimum external components. Typically, voltage regulators can furnish a constant output of 1 or more amps of current with a high ripple rejection. That's the role of the regulator here. Three-terminal regulator designed for fixed output voltages require only external capacitor to complete the regulation portion of the power supply, which is shown in the next part of circuit. Filtering is accomplished by a large value of capacitor between the input voltage and the ground. An input capacitor, typically 0.1 microfarad or 1 microfarad, is connected from the output to the circuit output to the ground to improve the transient response. That is shown in the next part of the circuit. As you can see, this is the complete power supply part. We have a transformer here, and so this is the AC circuit, AC input, and we have a switch here, and we have fuse. Then comes a transformer, and here we have a secondary FA transformer. The secondary voltage from 120 volts, it is brought down to 12.6 volts AC. And we have a bridge rectifiers in which we use 1N4001 rectifier diodes. All these diodes are 1N4001 silicon rectifier diodes, and the output of this is fed to the filter with a capacitor value of 6800 microfarad capacitor, and that is given to the 5 volts voltage regulator, and across this another capacitor is used to smoothen any ripple present in the output of a regulator. And now regulator output is constant 5 volts DC voltage. Okay, that's how the overall power supply, DC power supply, looks like. Okay, so this is a basic 5 volts regulated power supply. Now let us work out on the two formulas which are very important. One is line regulation, another one is going to be the load regulations. These two regulations are called as figure of merit of the power supply. So the regulation is expressed as a percentage, and it is a figure of merit, and it is used to specify the performance of the voltage regulator. If you want to know how voltage regulator operates, then it is better to look at these two parameters like line regulations and the load regulations. Line regulations specify how much change occurs in the output voltage for a given change in the input voltage. So this is a definition of a line regulation, and it is typically defined as a ratio of change in the output voltage for a corresponding change in the input voltage. Okay, so that is the formula to calculate line regulations. Okay, so it is delta V out. It is a percentage change in the output voltage to the percentage change in, I mean, the small change in the input voltage multiplied with the 100. So it is expressed in percentage. Load regulations. The load regulations specify how much change occurs in the output voltage over a certain range of load current values. Okay, so this is the definition of load regulations. So usually from minimum current or no load, NL what we call, to a maximum current full load. So the load regulation is calculated. The formula to calculate load regulation is VNL, voltage at no load condition, to the voltage at the full load condition divided by the V full load, and it is multiplied with the 100 to calculate in percentage. So these are the two performance parameters of voltage regulators, and we have a one related problem. So here again 5-volt regulator is measured with no load output voltage is 5.18 volts and the full load voltage as 5.15 volts. And what is the load regulation expressed as a percentage? So straight away we can substitute in this formula and calculate, substitute as VNL and VFL, and that gives me 0.58% as the regulations, okay, the load regulations here. So with that, we have come to an end of this today's lecture, and I hope this lecture is useful to all of you. And if you have any questions, maybe we can spend 1 or 2 minutes of time to answer the queries related to the points or the topics which were discussed in today's class.
Yes, sir. The ripple thing is there in the DC charging stations nowadays available.
Is it so?
Is, no, I'm asking, is it still there or it will be pure DC?
No, we need to calculate. See, the ripple formula, what it tells you is, so let me go back to the ripple calculations. Okay, these are ripple calculations. We need to calculate. It is actually the performance of the a filter circuit is output the losses, whatever losses which are happening here. So that can be calculated based on ripple to the DC voltage. Okay, so therefore ripple is nothing but the AC voltage to the DC voltage. So the VR peak to peak by VDC value. That is how the ripple is calculated. Okay. You mean to say that you asked me whether ripple is automatically calculated?
No, sir. Like I was asking if the DC which we are using nowadays,
Okay.
DC charging stations,
Yeah, yeah.
is it pure DC or like?
See, always
there
we
may
can't
be
expect a
variation?
pure DC in any conversion process. Okay, there'll be the 5%, sometimes the 3%, 2% like that AC will be there, but still the the circuits which requires fully DC can have a tolerance of up to 10%. That's how circuits are the manufactured. Okay, though it is completely DC, it expects, but still 2 to 3% variation it can tolerate. We can't expect 100% DC in any conversion process. Okay.
Thanks.
Yeah. And any questions or? Okay. If you don't have any questions, I just stop this lecture and continue the next topic with other the regulators in the next class. Okay. Thank you all for watching this.